I think we can get started, right? So thanks everyone for making the effort. I was myself was thinking, should I take all the walking and come here? But okay, let's get started. Thanks to the session of KubeEdge Deep Dive. My name is Sean Wang. I've been working on the edge computing area for the past 2+ years. So KubeEdge is like many other open source projects, has its roots from a commercial product, commercial cloud service. I want to give a little bit of background about that to help understand how we got here today. So about 2 years ago, a group of us, Jason and me and others, we started looking into edge computing, and immediately we found it is an area of great potential. So that's we went all in for it. And as a result, in April of 2018, we shipped our first cloud edge computing platform in China. It's a product called Intelligent Edge Fabric, or IEF. So this product has been, the service has been pretty successful. As an evidence, I want to share that in one of the deals that's already been signed and under deployment now, we are going to be running close to 250,000 of containers on edge nodes across China in the next few years. So I think for a edge computing platform nowadays, as a start, that's a pretty good result. And that certainly also gave us some confidence. And also because of our love for open source, we pushed this out end of last year to CNCF. I believe it's also one of the first edge computing platform. It's called KubeEdge. I think I see some familiar faces here. So today we'll be covering some of the functionality aspects of deep dive, and I'll also look at 2 typical application scenarios. So let's get started. Actually, one more thing I want to acknowledge. Today's session was supposed to be a joint session between me and Kevin. Kevin has been our open source front guy since the beginning of KubeEdge, and unfortunately he couldn't be here today, but I want to acknowledge his contribution and help with putting the content together. So we've had some basic ideas, but the main drivers for edge computing to become mainstream, these couple things. It's about reduced latency, and in this area, the major application types are first like machinery, industrial machineries that needs very fast and very reliable response. Or the other type is actually app that's getting very popular nowadays is TikTok type of things, where video sharing and video processing happens a lot on edge front. So that we'll see example of that. And the other type is the massive amount of data that even with 5G and all that future infrastructure, there's no reason to send this ton of non-structured data to cloud to be processed and stored. So that's the data aspect. And the third one, we actually, during our practice, found being a major consideration from a lot of customers is actually privacy and security, where individuals or businesses or government don't want to send store their information in public cloud or want to keep their IPs to themselves. So those are the major application areas. Here's an overall diagram. We've touched this yesterday. I want to just give a quick walkthrough so we have the background to start. KubeEdge is a Kubernetes application. We build 100% on top of Kubernetes. One decision we made is to separate the orchestration of Kubernetes from the computing side of Edge. And that separation gives us more flexibility later on to meet different business scenarios. I'll get into that later on. And on the Edge side, 2 main functionality. One is compute. That is get a container down and start running. So there's more detail of that. And the other part is about connectivity, because edge computing, two major scenarios. One is compute, like we said, video transcoding and so on. The other application type is IoT, where sensors that generates magnitude higher level of data than the traditional IoT we're seeing more and more of that. And also there's being able to connect all these different sensors is one of the big burden in all this IoT or edge computing type of development effort. So we have a full flow of solution for that. Start from the basics, how we build it. We have this in mind that we want to build a modularized framework that is open and expandable for future scenarios and technologies. So that applies to both our core and our application model. On the core side, this whole app is built on top of this thing called Beehive. There's probably 100 different beehives. This is yet another one. It uses Go channel. It's in the same GitHub under KubeEdge. So it is a messaging framework, and the basic module of that is module. And modules can be put into groups. And any new modules or new functionalities can be implemented by adhering to this interface. You have a name group, start and clean up. Then you will be able to get onto the platform and start running and talk to others. The other approach we've taken, we've seen other open source projects also start to do the same, is we build all the binaries, all these different modules into one binary and start with one process. And at the start time, you could simply use a config file and say, based on my business scenario, I want these 3 or 5 or 1 module running on this particular node instance. And that gives us the flexibility, the cleanness of just one process and one binary, and also the benefit of keeping the footprint to the minimum, because as we know, edge computing computer resource is limited, even though it's already a lot bigger than before, but we want to save that for the critical business applications. Same thing applies on the application side. To start with, you would package your logic into one container and push it down to the edge side and start up running. Then gradually you would say, I want different functionalities. You would have multiple containers running on the same node. Then in areas, you would have multiple nodes to support a bigger area or a campus or multiple things on the long road, or all these different scenarios. Then you would all of a sudden realizing you're in a microservice situation. And for that reason, we lift one level up from just containers to services. So I'll be talking about some details of Edge Mesh, which is a module we built for service mesh. You can do service discovery and call service nodes in between pods and connect them either node to node or node to cloud. So we'll see some of that as well. There'll be a couple of topics. I'll be jumping through each one of them. I'll try to make them clear. So this slide, I want to clear some air. There's some discussions in forums and others talking to us, asking what's the difference between just a kubelet, right? I think it's pretty clear with the overall architecture already. I just want to emphasize that what we do here is a full-fledged platform for edge computing. Its overlap with kubelet is actually in this box in the center marked as Edge D. If you look at the code, it is actually taking the kubelet code and get rid of the part we don't need and plugged in our code to make it work. So then on top of that, we build local persistency for reliability. We build edge cloud communication channel for management and for application data bus. We build device trains and device modeling for connectivities and device management and so on. So it is more than just a client. All right, so this is the next topic. I talked about separating orchestration and So in the first diagram, let me jump back a couple. And here you see a clear line where we see orchestration, or the upper part, which we said is in the cloud, and the bottom part is edge. Now, the reason for that, we want to make this clear separation of orchestration capability versus compute functionality, because in a lot of scenarios we see, it's actually a box this small, or even smaller than that, that's actually running all these modern software stacks. So we want to have a capability to manage really large number, hundreds of millions of such nodes in the cloud, and B, to save as much resource as possible. So we'll talk about a couple of variations this architecture can actually support. But since we separate compute and orchestration, some of the technical details emerges. For example, how to create a persistent volume becomes one, right? In a Kubernetes world, all these things happens locally in the same data center where you make a call. The persistent, the PVC, the claim actually is a synchronous call, which the external provisioner will call the local drivers, and till it gets the item provision, it will return. But for our case, we have to do it differently. So in this flow, you see that starting from step 1, 2, 3 are typical Kubernetes operations. Then from step 4, it's actually calling into a proxy driver we provide. And the function of that is to take this call, send it, if you look at step 5 and 6, send it to the Cloud Hub, then push down through our build channel with WebSocket or Quick, through that channel to the edge node. And there, it follows down to edge D, which is the computer provision module, where it calls the Kubernetes built-in volume plugin, and then calls the local third-party driver to actually provision this storage. And it goes all the way back up and to step 16 or 17, that finishes the full synchronous loop. So similarly, for a delete, it happens roughly the same. I think other than the name is the delete versus create, everything's almost the same, so I'll skip that. So that just shows the effort we have to do. But once we have that clear separation, good things can happen, because we now have the capability of not only running a KubeEdge local deployment scenario, we can easily put the orchestration part in the cloud and the compute hundreds of miles away, or we could have them moved or in different scenarios. I have a slide to talk about that. The next thing I want to talk about is edge device management. I've talked about the importance of it. We can do full-fledged device connectivity, modeling, shadowing, and sync up to Kubernetes, the full flow. And we use the Kubernetes CRD to do this, so it's 100% compatible. Basically, there are two object models we use. One is the device model, which describes what a device is like, right? And once you have that, it's an object model. You can inherit that and build a device instance. And that instance is used to store each device-specific information. So a flow of creating a device from the cloud is clear. You would use the CRD, create your own definition of a device, be it a thermometer or a camera or anything else, and push that into Kubernetes, and that will get propagated down to the edge side. On edge side, we do a couple of things. We build a device twin model where we actually shadow the device itself as a digital copy, and then we build a full flow of connectivity through a containerized mapper. This mapper's use is from the bottom device up. The mapper is used as a connectivity module to connect and convert the thousands of different protocols into MQTT, and you could actually even do some additional logic on top of that, and filtering and other things, and then pass this through a MQTT broker into an event bus, which is our MQTT messaging pass on the edge side. And this will further get into the device train, be modeled there and persisted there. And same information will be passed on to the cloud. So that's a pretty convenient way. And so far, we've implemented a couple of them, the protocol conversion plugins, OPCOA for industrial scenarios. It's a standard there. There's Bluetooth and there's Modbus. So, and the mapper itself is in a daemon set container. And we wanted to do it this way because eventually we want this to be a secured and fully isolated using Kata or other containers. So because Edge itself is already outside of data centers, and then this device connect plugin becomes another layer of security exposure, so that these separate secured containers eventually will be providing good security to all these safety attack scenarios. Now, I talked about device train. A device train, in our case, we actually referenced and borrowed the Mozilla's Web of Things definition of device train. It has three basic components. A device is similar to what a device is. A device attribute, which is a property bag of each attribute, its value, and its version, and so on. And a device train, which is also a property bag, but the difference is for a device train, you have two changing updatable state, an expected state and an actual state. And the flow of how this works is actually asynchronous. So on the right side, we have this diagram shows how a typical operation to set a device status from the cloud happens. For example, if you want to change a device from a sleep to an active state, right? That happens with setting up the status in Kubernetes, and that gets put down to our cloud, the device manager, and device manager then sends this information down to the edge side, where it's get pushed into device train. That's step 4. And after that, this operation is considered complete. Now, we know that devices are operating on a totally different pace. Some of them are always online, but some of them are not frequently online. They can be online for every second, minute, or even days, right? So then what happens is, move to the right side, you see device connects to mapper, and on step 5, mapper would go through a MQTT pub/sub model and try to get the new expected state change from device train. So that's step 5 to broker, 6 to the event bus, and event bus pulls from the device train. And that information then comes back, and the subscriber gets this information through mapper. And by this point, device knows it's expected to be in the active state, and that's when it happens. So definitely pay attention to the asynchronous nature of this operation. And similarly, for a set of actual status, for example, your device status changed by itself, the same routine of going through MQTT pipe and updates the device train and then get put up to the Kubernetes. Edge mesh is the next topic. We talked about this is the implementation of service discovery on the whole service mesh front. What we've implemented is actually something that will enable you to, first of all, write in ways of fully cloud-native programming where you're talking to services in a microservice infrastructure, right? A node from a pod or a application instance from one pod could talk to a service that's distributed on the rest of the deployment. So here's a flow of how this works. The blue side is actually the control flow. Basically, you would configure a service, a Kubernetes service, and associated pods with that service, and that information is passed from the top into the edge node and persisted there. Right? With this information, if in case a application wants to reach a service. Like here, there's a little bit of confusion. This HTTP/B/resource B refers to another service, but then there's a pod B, so ignore the pod B, just consider B as a service. Then what happens is we actually, on the pod level, set up a proxy which hijacks the traffic and we maintain a DNS service internally of our own, and that resolves a L7 or L4 namespace to a service name, and which in turn hooks up with the service information that's passed down to land some rotation rule on a pod, and so you can finish the logic. And similarly, we don't want to limit this to edge nodes to nodes only. Currently, the code works for nodes within the same subset, different nodes. But eventually, we want this to be able to be a protocol or practice that can be used for nodes, cross domains, or nodes and cloud services type of communication. So in this case, you can see that with a router, the same logic can be used to go through the edge cloud boundary and actually reach a service in the cloud, which is a very typical scenario we will see later on in the application. Okay, so time-wise, I have 21. A couple minutes on application scenarios. So through the practice, we talk to all the different type of customers and understand their needs. What we've found, customer has a lot of ideas, right? And it's really based on reality of what they have and what they want to achieve. The left side is very typical Kubernetes implementation that you have orchestration fully on the cloud, and then you have just very tiny boxes running specific logic at each location, for example, a convenience store, a campus, a roadside box, and so on, right? So that's a typical KubeEdge scenario. The other one is the one in the middle where you pretty much don't want to deal with cloud component at all. Instead, you just want to have a deployment that's local, right? But Kubernetes itself may be too big for it. So we see applications such as K3s kicks in this scenario. That also works, but it's a completely a private deployment without utilizing the cloud power. And then customer will say, hey, I have a business where there's trade structures of organizations and headquarters and so on, and how do I deal with that? I think KubeEdge, by the way, can deal with all these scenarios easily because we have this clear separation. We can just plug the computing modules to a different orchestration engine, right? So we've seen requirements in reality for all these scenarios. So that's why we think the architecture is a good one. It's open and it's very flexible. Now, two real application scenarios I want to talk about. One is a IoT scenario. In this case, a smart city would, this is actually more of a traffic control type of scenario where a couple of edge nodes will actually form a small cluster. Sometimes a single node actually connects to multiple cameras, a specialty camera to read the license plate, or just a car, outline of a car. And there's cameras that take video of a road condition, of traffic, how many cars are there, doing stats on that. And then there's maybe the same algorithm sitting on the same stream, but trying to detect if there's any illegal crossing, any other situation, dangerous situations. So this kind of app is getting more and more popular. What you can see here is there's a clear edge component which runs intelligent algorithm to actually carve out car shape or picture of the car, carve out the license plate, but then send the information to cloud through a constant connection. And in the cloud, more complicated logic or heavier service can be called. For example, you want to search a national database or some registration about the license plate, if it matches the car description, if there's additional issues with that license plate, and so on. Or connect multiple such edge nodes and find out the traffic pattern and find congestion trends and so on. So this is a very typical and very useful scenario. It cuts down dramatically the amount of data that needs to be sent to a central cloud, and also because it's on-site, it's very efficient. Cost-wise, the network bandwidth is a major cost in many of the scenarios. And we see a clear pattern of edge and cloud coordinating and working together. We actually have a term for it called edge cloud synergy. And another aspect of this is, even though it's behind the curtain, but there's a heavy training, as you all see, that for all these scenarios to actually happen on the cloud with the unlimited compute resource before you could actually implement all these things and keep improving them. So the loop is continuous improve, training, feedback, and improve, right? Second scenario, I talk about TikTok, right? We've talked to customers in China and worked on prototypes and POCs with them. It's actually popular in Asia, now getting more and more popular here as well. So the challenge here is this. Large data centers have unlimited compute resource, but it also has a network connection. Even though very large already, it's precious, right? So you don't want to spend 70% of that sending all this video data. And also, the cost is much higher for network charge from a edge node or a CDN site compared to a major data center. So what happens is more and more business of this video sharing type of application moves such logic onto CDN or edge sites, where you have edge network cost that's 1/5 of, or even less than the large data centers, and you have compute resources there that's very close to where the content providers are. There's a clear pattern here. For example, metropolitan cities will have a lot more content providers and viewers than the rural areas, right? So there's a concentration. So if you have more compute resources in those edge nodes, that solves the problem locally. And in this case, you could also add additional value-added services such as content detection to make sure things are legit, legal, and or at least appropriate, right? And KubeEdge in this scenario works well because in this case, one of the benefits to KubeEdge is there's a very strong constant connection and there's resources there. So when something happens, the connection even fails, those nodes can still work on its own because it's not hard to bring up a backup orchestration engine and keep the business running. So I think that wraps up the talk. We want this project to get more participation, so follow us on Twitter, scan that, and there's a lot of information you can find on all these different channels. We think this will be an area of great interest. So I have 5-7 minutes, so any questions are welcome. Try to answer. So right now we can run as small as 70 megabytes to start the engine, right? And because right now we only support container, that's we could potentially even cut it that smaller if you just want to run a process. We have plans to run either process or VMs through the orchestration engine. So that can, to a current day ARM or Intel box, even if it looks very small, normally it would have a couple gig of memory, so that footprint is pretty small already. But then once you start running, just add a little bit, you have the containers and you start collecting logs, the footprint will grow a little bit, but it's still much smaller, and we have the machine learning scenarios running no problem. Sorry.
So coordinated orchestration.
Yes.
What does that mean?
It's a really, really good point. So customers want all the, you're asking coordinated orchestration, the meaning of that. So let me go back to this, this slide. 1 and 2 are very simple. the one on the left says, I want orchestration simply in the cloud, right? Scenario 2, I want everything all together in a private setup. But customers sometimes say, hey, well, I have no problem provide the internet connection, but what if in cases the connection will fail, right? In this case, KubeEdge already provides the capability to keep the business running continuously without interruption, because with the local data cache and everything, we can bring up a container if it's crashed or restarted anything. So that's no problem. But customer want more. They say, what if I still want some orchestration capability because, hey, now I have 4 machines here, and sometimes I need to jiggle task a little bit. So I think in that scenario, there is a chance we can, because we have the separation between Cloud Hub and Edge Hub. So on the interface level, we only need to direct this Edge Hub to another orchestration endpoint. Certainly, the more work behind that is how do you sync the data and so on. So that needs to be solved. I think it's completely solvable because, as you can see, we have a channel there, so while the channel is open, you can actually have that data down and kept as a backup, and then when it needs to switch, you can just switch in.
Does it mean, for example, if I want to have the people who stay stuff on the edge, I have to have some kind of mini cloud hub running?
Yeah, so because all that happens is we're going to run the cloud edge, and the cloud core is basically a channel pipeline controller that talks to Kubernetes, right? So this transition should be pretty straightforward. I mean, it needs some work, but it can be done.
So it's still like not really feature.
Feature-wise needs wiring. We haven't really get to the point to actually implement this, but architecture-wise, it's there. Yeah.
I have 2 questions. One is related to CNI. So what kind of CNI is used in this case?
CMI?
CNI.
Oh, CNI. I believe we support the standard CMI, but CNI, I don't know the detailed version of that. So the question is, what's the CNI version, right? What type that we support? Yeah.
What type? So if you are using
I've
by default supports Plano, but
Yeah. I've seen people, actually, yesterday I went to a talk, there's a guy actually used Plano, and I personally tried it on AWS with AWS network support. So, and there's a list of supports, because these things actually is part of Kubernetes. So for at least the 2 I tried, they all work, so I would assume other things shouldn't be too hard. Yeah, but I could be wrong, so send me information if you try something and found there's a problem.
and the related question is what kind of load balancer
Ah,
because with Edge and those things involved,
yes,
you have different kind of load balancers.
sure. Sure. So the question is what kind of load balancer you use. Internally, if you drill down the code, it actually uses another component called Go Chassis. That's also an open source project you can find on GitHub. Go Chassis implements a couple of basic round robin and other algorithm, but this part is basically pluggable. We actually have plans to integrate with Istio, so that you could actually be controlled by Istio as well. Go Chassis. Go dash chassis, like a car chassis. Yeah.
And one final question.
Yeah, go ahead.
So have you also considered virtual kubelet because as a substitute for HD, because it can do some of the things like it can offload
Yeah.
kubelet
Yeah.
work,
Yeah.
some remote thing or cancellation.
Yeah. I think conceptually they actually do very similar things where you sort of just have a thing very close by. The actual work happens 100 miles away. So we'd look into that. I think it's a possibility. Yeah, it can definitely work.
How do you have connectivity between edge and the cloud?
Okay. The question is how do you keep the connectivity between edge and cloud. So all the connection are issued from edge because the network situation, the best you can do is start a external facing outgoing connection, right? So we implement a WebSocket implementation for the connectivity or quick. Both are there, QUIC. They're both bidirectional. So you can pass on different message types or implement different protocols on it. Okay.
So there's a clearly concept of device,
Yes.
very strong thing
Yeah.
in this solution.
Yeah.
So device is usually kind of that thing that just gives you something.
Okay.
And you have some kind of application. Can we have like a node that's also a device?
Yes.
In the edge?
Yes.
Like a more capable hardware that also has some like cameras or sensors attached to it?
You're right. Conceptually, a node is a very powerful device. Yeah. So as a modeling, as a concept, that's a hierarchy. We make them separate so people are easily can understand this and work on this concept. So because often cases what you're dealing with is a compute module connecting to a bunch of sensors. Those are called devices, and they will be managing the state and retrieving data and processing them to finish the business logic. So you're right. Logically, that node is a device. Yeah.
So for a particular word case scenario, can I say that this device is also capable of doing compute, but also capable of receiving sensor information, but somehow I want to logically assign this compute is related to this particular sensor device. So
Okay.
the compute that executes on this processor is related to the data it receives, is local to the data it receives.
Okay. Okay. I forgot if I repeated the question. The question is basically asking, is compute itself, the edge node itself, a device? The answer is yes, and then this gentleman is further asking, what's a better way to define or module a compute, right? If it's in an object model type of design, you would say everything is a device to start, right? Then smaller devices or simple devices would just have attributes and a couple of operations, and a compute device would then expand on its compute nature of things. I would start from there, and it's the purpose of this to really unifying everything and talking one tone of like object-wise as a device. Is that the goal?
Well, the purpose is more like the local locality of data.
Okay.
One device which is capable as a compute, has a camera, video, data input,
Yeah.
the same local device. So instead of moving that data across the edge nodes, we would prefer to process it on the actual.
Got you. So currently it works this way. That's a really good question. So it's about vicinity of your computer resource versus where the device really is, right? So what we do is in current setup, a device will actually have a link reference back to which compute module it belongs to, right? But then there certainly comes a question of what if this compute module dies down and you can still access the device through the network, right? So currently we would be pointing that pointer to another compute node and to reach the balance. But similar thing can be done with the load balancing to consider some of the vicinity factors to see, let me choose the one that's closest to me instead of calling a node a couple hops away. Yes, preference based on, distance or something. Yeah, thank you.
This edge mesh is within the node, or we can communicate?
Good point. Question is edge mesh within the node? Answer is yes. It's different from the sidecar concept. So we maintain a module. So all these concepts of the whole edge core is inside the node. So it's edge mesh. So they actually hijacks all the traffic for that node and process from there.
But what about the other node? How do the two parts of the two different nodes
So here, coming back to this chart, you would be, oops. You would have the concept of service, and the service would group these pods together. They would be able to tell this service runs on this 1, 2, 3 pods on these 1, 2, 3 nodes. And once you have that information, what you're doing is actually finding what the service it is trying to call, get the 3 nodes, get the 3 pods, and try to find the next one or the proper one and send that, hook that up. Yeah. Does that make sense? Okay. No, for node to node within the same subset, we will just connect them. Yeah, we'll just build a channel and connect the two, and it'll be done. Yeah. Oh, I was explaining this. This is module is a framework we use called Beehive. We have our own Beehive. That's a Go channel-based communication mechanism. The basic function block on that is a module. So let's say I want to build a edge mesh. I want to build a IP lookup or something. Each one will be defined as a module, and that module needs to implement these 4 interfaces. And then you can use it across the system to talk to other modules. Like here, once you've done that, you just simply say send to edge D, which is yet another module, and this is my information to send to. Yeah.
How would you consider the life cycle management of that device itself helping this edge framework? Because it requires push notification rather than pull mechanism, right? So,
Yeah. Well,
do you consider any framework to support that push kind of framework?
Okay. So the question is, how do you manage device lifecycle? Basically, I believe, correct me if I'm wrong, I believe we have the capability to do that already, because there's a couple components in here. First, the MQTT protocol is push and pull, but inside Edge core, we also have a device controller, which actually subscribes to all these different topics, and it itself also holds a list of topics. So it'll constantly look for information, status change, and everything, and facilitate the information passing either to the cloud or to the device. So is there an aspect you're thinking of? Okay. So status change of a resource needs to be reflected, right? Yeah, I think that's what we do, because on the Kubernetes level, all these objects with list and watch, you will be able to sense any of the status change, right, for other objects as well. So I believe you can do that. This shouldn't be a problem. Similar thing, if a pod falls out from a service, that should be noticed as well. It should be sensed and pushed down from one node, push to Kubernetes, and then push down to all the rest of the nodes.
What happens if
Do we still have time? I don't know. Go ahead.
What happens if edge core is not able to connect to cloud?
Yeah, in this case, bottom line, all functionality continues, even if a module or a pod crashes. You would still be able to use the local cached metadata and the local cached image to bring it back up. So that's the minimum. So business will keep running. Eventually, we need you to come back. Or we have a component called Edge Site, which is a orchestration engine just like K3s. You could run that, and that'll give you the orchestration capability. Cool. Potentially. Okay, thank you guys.